Many chemical reactions that we will be considering in this course occur in solution. So before we proceed to study them, let's take a close look at what solutions are first. By definition, solutions are homogeneous mixtures of two or more substances. Unlike in chemical compounds, where according to the law of constant composition, the ratios between different elements are always the same, the substances, whether atomic or molecular, that compose a mixture can be combined at arbitrary ratios. The term homogeneous means that all substances that compose the mixture are present everywhere within its volume at the same ratio. Solutions that consist of only two substances are called binary. The more abundant substance in a binary solution is called the solvent, and the less abundant substance is called the solute. For example, if you dissolve a teaspoon of sugar in a cup of water, the sugar is the solute, and the water is the solvent. Not all substances can dissolve in one another. The ability of a substance to dissolve in another substance is referred to as the solubility. When we speak about solubility, it is always important to specify both the solute and the solvent, because most substances are soluble in some substances but not in others. For example, it is insufficient to just say that sodium chloride table salt is soluble. We need to specify in which solvent it is soluble. In fact, table salt easily dissolves in water, but will not dissolve in, say, olive oil. The correct statements, therefore, would be sodium chloride is soluble in water, and sodium chloride is insoluble in olive oil. A very wide variety of chemical substances can serve as either solutes or solvents. For instance, gold is insoluble in either water or oil, but it is soluble in aqua regia, which is a mixture of hydrochloric and nitrous acid solutions in water. A fact known already to the 9th century Persian alchemist Muhammad ibn Zakaria al-Razi. In fact, although people commonly think of solutions as being liquid, that is not necessarily the case. The definition of solutions, homogeneous mixtures of two or more substances, never makes any reference to the aggregate state of the substances. So, for instance, air can be considered a gaseous solution that consists of nitrogen, oxygen, argon, carbon dioxide, water vapor, and small amounts of other gases. Marshmallows are a solution of air in a solid. Metal alloys are solutions of various metals in each other, or of nonmetals in metals. For instance, steel is the solution of carbon in iron. Different types of steel may have different content of carbon, but it is always considerably less abundant than iron, making up no more than 2.14% of the total mass of steel. Because the content of carbon in steel can vary, steel is not a chemical compound, it is a solution, a mixture. Thus, in this solution, iron is the solvent and carbon is the solute. As you know, at room temperature, steel is solid. It's a solid solution. Water is the most common solvent both for naturally occurring solutions, such as seawater and bodily fluids, and in chemistry. Solutions where the solvent is water are called aqueous. Water can dissolve a wide variety of substances, though not all substances. For instance, it does not dissolve oil. It is a readily available and non-toxic solvent, and aqueous solutions are relatively easy to handle, measure, and mix, so all these factors make aqueous solutions incredibly important and widespread in chemical labs and the chemical industry. Both molecular and ionic compounds can be soluble or insoluble in water. Let's consider a few examples of molecular substances that are soluble in water. Oxygen, O2, a diatomic homoatomic gas, can dissolve in water, and many marine life forms such as fish can breathe this dissolved oxygen. Ethanol, C2H5OH, a molecular liquid, can also dissolve in water. Vodka is a binary solution of ethanol in water. Sucrose or table sugar, C12H22O11, a molecular solid, also dissolves in water quite easily. When these or any other molecular compounds dissolve in water, the molecules that make up the substance separate from each other and are surrounded by water molecules. However, all atoms that make up each molecule remain bound to each other, so each molecule itself is intact. In contrast, when ionic compounds dissolve, water molecules pull the ions that make them up apart. This process is called dissociation. For instance, in an aqueous solution of sodium chloride, table salt, the sodium plus cations and chlorine minus anions float around in water independently. If an ionic compound contains polyatomic ions, then when the compound is dissolved, the cations and anions separate from each other, that is, dissociate. However, the atoms that make up a polyatomic ion remain bound to each other. For example, when we dissolve silver nitrate, AgNO3, in water, we get Ag plus and NO3 minus ions floating around independently. But the nitrogen atom and 3 oxygen atoms that make up the nitrate anion remain bound together by covalent bonds. An interesting side note is that because aqueous solutions of ionic compounds contain ions that are electrically charged and can move independently from each other, such solutions can conduct electricity. When an electric voltage, for instance from a battery, is applied to an aqueous solution of an ionic compound, the positively charged cations and negatively charged anions begin moving in opposite directions. Such directed motion of electrically charged particles is nothing else than an electric current. Therefore, solutions of ionic compounds could be used as electric wires. While it is not practical for household applications, the ability of ionic solutions to conduct electricity is used in some industrial processes, such as electroplating, the deposition of thin metal layers on surfaces of other metals, either for decorative purposes or to prevent corrosion. Because of their ability to conduct electricity, aqueous solutions of ionic compounds are also called electrolytes. Solutions of molecular compounds do not contain charged particles because atoms in molecules are covalently bound and remain bound together when the molecular compound is dissolved, and molecules are overall electrically neutral, and therefore solutions of molecular compounds cannot conduct electricity. It is not always easy to determine whether a given solute dissolves in a given solvent. This information can be found in special solubility tables, and you will always be able to look it up. However, it is good to remember a few general trends that are summarized on the slide. Any ionic compound that contains the alkali metal cations lithium plus, sodium plus, and potassium plus, or the ammonium polyatomic cation NH4 plus, is water soluble. So is any ionic compound that contains the nitrate NO3 minus or acetate C2H3O2- polyatomic anions. Most compounds that contain halogen anions Cl-, Br-, I- are also water-soluble, except for compounds where any of these anions are paired with silver+, mercury 2,2+, or lead 2+ cations. Most compounds that contain the sulfate polyatomic anion SO4,2- are water-soluble as well, but the following sulfates are not: calcium sulfate, strontium sulfate, barium sulfate, and lead 2 sulfate. On the other hand, most hydroxides, sulfides, carbonates, and phosphates are not water-soluble, but there are some exceptions. Most notably, when the polyatomic anions in these compounds are paired with cations that always cause an ionic compound to be water-soluble, lithium+, sodium+, potassium+, or ammonium NH4+, the resulting compound will be water-soluble. In addition, calcium sulfide, strontium sulfide, and barium sulfide are also water-soluble.